Welcome to Spring LIB.
So we know that energy of a photon is given by Planck constant h times frequency of the photon, and frequency is speed of light over the wavelength of the photon. Hence energy will be equal to hc over lambda, where we substituted f to be equal to c over lambda. Now in the first part we have to find this frequency, so we will use this equation. So F is c over lambda. We know the speed of light, that is 3 times 10 to the power 8 meter per second. Lambda is given to be 600 nanometers, so we have to convert that into meters in order to substitute that into the equation, and this gives the frequency to be 4.9965 times 10 to the power 14 hertz. Now, for the second part, we have to find a number of photons. So, we are given the power to be equal to 75 watts, and we know that power is energy per unit time. So, if power is 75 watts, this means that energy of the photon is 75 joules for every second, or for t equals to 1 second. So for that amount of time, let's find E. So energy of a single photon is, as I wrote over here, so we will use this equation hc over lambda, and this can also be written as h times f because we already found the frequency, so we can directly use this answer over here. And h, the Planck constant, is 6.626 times 10 to the power minus 34 joules seconds, and then we substitute this value of frequency, that is hertz, and this gives energy of a single photon to be 3.3107 times 10 to the power minus 19 joules. So now we know the energy in 1 second, and we know the total energy for 1 second given by E, and we know the energy of a single photon, and we need to find the number of photons emitted by the source in 1 second. So, since this total energy is formed by the total number of photons, so we can say that the total energy is n, where n is the number of photons in 1 second times energy of a single photon. So n can then be found by dividing the total energy for 1 second, that is 75 joules, over energy of a single photon. And substituting these two values, we get n to be 2.265 times 10 to the power 20. And n, as I said, is the number of photons emitted by the source per second. Since the energy E that we used was also for 1 second, therefore the number of photons that we got is also for 1 second. So that's the answer. Now in part C, we have to see if the answers to part A and B are same, and is the frequency of the light the same thing as the number of photons emitted per second. So the answer to the first part of part C is no. The number of photons emitted per second is equal to the power, while the energy of each photon depends on its frequency. So obviously the first part is no, because the answers to part A and part B are not same. And that obviously means that the frequency and number of photons emitted per second is they are not equal. So number of photons emitted per second is proportional to the power, and the frequency is proportional to the energy. So that's how these two differ. Also, the frequency of the light, as I said, is proportional to energy. So it depends on the energy of each photon, and n, which is the number of photons per second, since it's proportional to the power, so it depends on the power output of the source.